Good afternoon. Today's lecture is a rehash of what we did about a month ago, talking about how the compositions that we measure within different types of meteorites record the effects of fractionation of both elements and isotopes. So remember, fractionation is the process of separation of elements by virtue of different types of chemical and geologic processes that produce these separations. If we keep it in mind, we're using the composition of the sun as a baseline to see how different types of fractionations produce the compositions we see. We recognize fractionation can occur as a consequence of condensation, that is the production of solids from gases. We recognize that fractionation processes record volatility controlled processes, or those that are a consequence of temperatures. We recognize that physical processes that separate different phases of liquids from solids or gases from solids can also produce fractionations. We recognize these can occur during magmatic processes such as differentiation or fractional crystallization. We also recognize the effects of chemical fractionations as a result of surface processes like precipitation or evaporation. And then finally, we recognize fractionation can occur as a result of pre-existing processes leading to materials inheriting compositions based on fractionation. This slide shows two examples of fractionated compositions measured in different meteorite types. The graph on the left, we're looking at the ratio of volatile to refractory compositions of elements. And we see that the vertical and horizontal lines represent the solar composition, or in this case, the composition of Ci carbonaceous chondrites. What we can see in the graph is that chondrites are fractionated relative to the solar composition. Some chondrites, such as the El chondrites, show enrichments of volatile elements, whereas many of the other groups, including the CV chondrites, show different fractionations showing depletions of those volatile elements. We see that the achondrite groups, or groups of meteorites that are derived from planetary differentiation, also follow that volatility trend. With respect to these meteorites, these are born from magmatic processes, and the elements we've chosen here, rubidium and strontium and potassium and uranium, are somewhat immune to the effects of fractionation during magmatic processes, and thus record fractionation effects that are part of the true precursors of these meteorites. On the right, of course, we see the triple oxygen isotope graph showing how meteorites are formed in regions with different oxygen isotope compositions. What this implies is that that something acted to fractionate these oxygen isotope compositions prior to the formation of these meteorites. Now, these graphs show the bulk composition of volatile and refractory elements. You can see volatility is measured as a result of 50% condensation temperature. So the vertical dotted lines segregate refractory compositions on the far right, volatile compositions, moderately volatile compositions in the middle, and highly volatile compositions on the left. If we look at the top graph, we're looking at the composition of elements in the interstellar medium, that is, interstellar space, not necessarily in a star-forming region. And what we can see is that these regions are enriched in volatile elements and actually depleted in refractory elements. If we compare that to a graph of the bulk composition of some of the major carbonaceous chondrites, we see that they show a smooth trend of depletion in the volatile elements and enrichments in the highly refractory elements. So our job as cosmochemists is to try to examine what are the processes that lead to these volatility fractionations. So one model says that volatility fractionations that are recorded in chondrite meteorites are the result of the processing that the precursors experienced while in the solar nebula during the time when the sun was forming. So, in other words, these precursors inherited their compositions from processing within our solar nebula. The precursor materials are dust and gas that was surrounding that localized area that went to forming the dense molecular cloud that would then collapse to form our sun. So as our sun cooled, it condensed solid matter, which would then be subject to processing to form meteorites with these volatility depletions. One of the implications of this hypothesis is that this allows for the different types of chondrite groups that show different volatility-driven fractionations formed in regions of the solar nebula with distinct temperatures. A different model hypothesizes that the precursor material actually inherited their depleted compositions before this material was processed by our solar nebula. In other words, the dust and gas was processed early before the solar system began its history, and these solid materials were then utilized, were then condensed during the early history of the solar nebula to solids that would go into forming the different meteorite types. This is just a cartoon showing a hypothetical dust grain that forms in the interstellar medium. We can see that it's an amorphous grain that has a silicate core. It may have various mantles of refractory organic materials, and typically these are surrounded by mantles of icy material that is rich in volatile elements. During processing, either in the interstellar medium or within the solar nebula, these icy mantles of course melt and release volatiles, but obviously some of the more refractory mantles of material will also experience melting and subsequently recondense. So this is a method to explain how we can form precursor materials that have inherited these volatility driven fractionations. Now we of course recognize that fractionation can occur during the process of condensation, and we utilize the condensation sequences developed for the crystallization of CAIs to help explain that. We can see that most refractory elements will crystallize highly refractory minerals, such as those seen here, that are some of the first phases that we find in the oldest solar system solids, the calcium aluminum rich inclusions. Subsequent crystallization will lead to compositions such as the minerals that we find in chondrules, olivines, and pyroxenes, with subsequent crystallization or condensation of solid material, forming the material that's similar to what we find in matrix materials of chondrites. Now we can see that relationship here. This is a graph showing the bulk composition of volatile to refractory elements that we measure within two different CM type of carbonaceous chondrites. What we see in the graph is there's three distinct plateaus of compositions that reflect the refractory elements shown on the right that are primarily measured within CAIs, the moderately volatile elements between chromium and nickel that we find associated with chondrules in the middle, and then finally the volatile elements that we find making up the matrix material of these meteorites. What it shows is the volatility, of course, controls the environment of formation, again providing another example that these rocks are mixtures of components formed in different regions of the solar nebula that formed at different temperatures. These are graphs of the bulk composition for the major types of chondrites, and what they show is the same smooth depletion in volatile elements. The carbonaceous chondrites show enrichments in the more refractory elements, those on the right side of the red vertical lines, but all the elements to the left of the lines show the same volatility-driven depletions. Now in this graph, the black circles are lithophile elements, and the open circles are siderophile and chalcophile elements. What we can see in the graphs from the HL, LLR, EH, and EL groups of chondrites is that the patterns of volatility depletions are different and thus represent different environments of formation where those rocks occur, where they first formed. If we look at a single group, like the ordinary chondrites, we see that there are even differences in volatility depletions of different types of elements. In this graph, the closed circles are siderophile elements and the open circles are lithophile elements. And between the different groups, the high iron to the very low iron, we see different depletions of siderophile elements. This again represents different environments where these rocks formed. Now, I mentioned before, there is something called Pryor's Rule, which is a group of observations about the ordinary chondrites and the presence of oxidized or metallic iron in these different groups. High iron chondrites are those that have a high abundance of iron nickel metals, which are actually have low nickel content in the metal grains, but they also have the lowest abundance of oxidized iron within the iron magnesium silicates, the iron, the olivine, and pyroxene. Now the LL chondrites have the lowest abundance of iron nickel rich metal, which in this case happens to be very nickel enriched and have the highest oxidized content of iron within olivine and pyroxene. This graph looks at those compositions in a different way. On the bottom, we're looking at oxidized iron versus silicon. On the y-axis, we're looking at the amount of metal. What we can see with all of the chondrite groups in comparison to Ci chondrites is they show a loss of metal. So there was a physical fractionation of the metallic component where they formed. On the x-axis, we see the effects of reduction versus oxidation, again showing that there were differences in the localized environment where the different types of ordinary chondrites formed, as well as the different types of carbonaceous chondrites. The carbonaceous and Rumerudi chondrites formed in a much more oxidizing environment, whereas there's a variety of increasingly reduced states where the LL and H ordinary chondrites formed. So we also recognize these volatility depletions in the achondrite groups, or the various groups of meteorites that were formed on planets that differentiated. So again, we see the graph of volatile to refractory elements on the left, showing the different proposed planetary bodies where some of these meteorite groups come from, and we see an increasing trend of depletion in volatile elements, with those from Mars showing some of the most some of the least refractory compositions, going up to a yet to be identified parent body for the angerite meteorites, showing the most refractory compositions. We see the exact same trend occurring in the iron meteorites, where we have the volatile elements germanium and gallium plotted against the more refractory element nickel, showing that the different types of iron meteorites formed in different environments according to volatility. This is another way to look at those fractionations in achondrite groups. If we plot two refractory elements, uranium and lanthanum, we can see that all the meteorites show the same basic bulk composition, and that there's a mixture in the refractory compositions. If we plot a volatile element like potassium versus lanthanum, we can see that the different meteorite groups separate onto different mass-independent fractionation trends. And we can see that they can be distinguished based on these different trends. We also recognize fractionations occur due to physical geologic processes occurring on the parent body, asteroids, and planets of different meteorite groups. One of the most obvious examples of that comes in the form of differentiated planetary bodies, where when we start to solidify a molten body, we form an iron-nickel-rich core, thus segregating that iron and nickel and other siderophile elements from the overlying liquid mantle. That leaves a net depletion of elements, especially siderophile elements, in the mantle and crust that are available to form those rocks. Another example would be the formation of the moon. Many of the large planets formed originally as wholly molten bodies or magma ocean bodies. In the case of the moon, one of the first parts to form was the metallic core, with the majority of the body being molten surrounding that core. As the moon's surface crystallizes, cools and crystallizes, first formed minerals are minerals like iron, magnesium, silicates, iron, and pyroxene that are more dense in the surrounding magma and sink to form the mantle. By virtue of those minerals crystallizing out, they remove iron, magnesium, and silicon from that overlying melt, enriching the composition in elements like silicon, aluminum, and calcium. And that's what we see forming the crust of the moon. My challenge to you guys is to tell me some other examples of geologic processes that produce fractionations that you could measure the compositions of. Thanks and have a good week.